Okay, let's get started since we're already a few minutes behind. So kicking off the afternoon session, we have Michel Devoret here, who will tell us about perspectives of millimeter wave quantum Josephson circuits for qubit readout and gate control multiplexing.
Okay, thank you, Monica. Okay, thank you to all the organizers for inviting me to this very nice workshop. It's giving a talk on millimeter waves, but I have to maybe issue a warning here. In superconducting qubits, what we call millimeter waves is things that are above 25 gigahertz. So compared with the talk this morning, where experiments were done past 100 gigahertz, I feel a little bit a weakling here, but I'll still tell you about our recent new ideas about the control of Josephson qubits at these higher frequencies. And before I go into the meat of the talk, I wanted to acknowledge several people here whose data I will show during the talk. There's an experiment performed by Pavel Kurolovich and Tom Connolly, together with Charlotte Bocher, who's now here starting a lab at Stanford. And this was also done with undergraduate student Elif Naz-Onda. I would like also to acknowledge a recently started collaboration between Debatri and Das, who is a student in Emilio Nani's group here, and I will briefly mention this during the talk. I would like also to acknowledge Hong Tang, who is a colleague at Yale, with whom we have recently collaborated on niobium nitride films, which I will also discuss. Okay, so this is the people here. Pavel and Tom are here. This is Charlotte here, and Elif Naz is here. And I would like to also acknowledge the collaboration we have with Leonid Glasman and with Vala Fatemi. Okay, so I would like also to make a little announcement saying that all this work that I will present has been performed at Yale, but my lab is diabatically moving. It will take months and months before it will fully establish, but we are forming a little group here already in Santa Barbara. Okay, so in my talk, I will try to address these three motivations, although the third one, which is to increase the operating temperature of quantum components, I will only briefly touch it. This will be covered, I think, amply by Dave Schuster tomorrow morning. So I will not discuss this. I would like to actually discuss this first motivation, which is that we've recently, as I will show, we've found out that, in fact, the qubit readout, which is so essential, is actually improved quite a lot if you go to higher frequency. And this is, by extension, true of all the parametric oscillations, parametric gates that you may want to do in superconducting qubits. So, and the second motivation that I would like also to discuss is this question of multiplexing that was touched on this morning. How do you limit the number of wires in the control of qubits? Okay, so why are we interested in readouts? Well, readout is absolutely fundamental for error correction. Readout is what allows you to essentially reduce the entropy in the system. It is the removal rate of entropy that is at the heart of error correction. In the surface code, it is done by all these measure qubits here, which measure stabilizers around 4 data qubits. And if you want to encode information using the Gottesman-Kitaev Prescale code, or GKP, you also need to remove the entropy as fast as possible. And in that code, it's done by an auxiliary Transmon qubit. Okay, and well, right now, the entropy removal rate is actually the bottleneck for error correction. Even in Google's recent experiment, well, you might think that in this budget, the 2-qubit gates here is the majority. This is not going to be valid very long, because as you reduce the errors of 2-qubit gates, you have this huge bottleneck of the measurement fidelity, which becomes more and more important as you improve the error correction gain. So really the question that we started to really work on a few years ago is how to eliminate these measurement errors and improve error correction. So what exactly do you need when you are doing error correction? Well, you have to have what is called a good quantum non-demolition fidelity, which means that you have to basically implement the textbook measurement axioms, which is usually not the case. So you need to, if you have state 0 and 1, you need to project the system, your qubit, on these states, 0 and 1, according to the Born rule. But that's not the only thing. You need also to report accurately what a state has been projected. So let's take a qubit, which will be the first 2 states of a whole manifold of levels. What you need is not only to know with certainty to report whether you were in 0 or 1, but also you want to avoid extra operations, like for instance, bit flips. You don't want the readout to actually do uncontrolled bit flips, but you don't want also to produce what is called leakage, measurement out of the computational space. And you want to, so it's not just, what I mean, it's not simply having two different histograms for your measurement outcome that do not overlap. You want basically to make sure that the states that are reported here are the states that the qubit has after the measurement. Okay, so we're going to specialize to the Transmon qubit, which is the electrical analog of pendulum here. If you solve the Hamiltonian of this system, which is essentially has exactly the same form as the pendulum, you get this ladder of states here. You have states in the well here, and the states above correspond to the free rotating pendulum. And you're using, for the Transmon qubit, you're using these first 2 levels here. And you're using the fact that the system is anharmonic, so basically, as you go up in the well here, the level spacing diminishes. Okay, so what you do is that you control this system with microwave. You couple this artificial atom to a transmission line, and you can send microwave and produce, for instance, Rabi oscillation. But when it comes to reading out, things get more complicated because unlike atoms, which you can probe by fluorescence, here, each time you are going to couple your artificial atom to a transmission line, you're going to damp this transition here. This is called the Purcell effect. So you have to be a bit more subtle, and you have to use an extra degree of freedom. So this is what we do here. I have taken the circuit and put it flat. You have one transmission line that you use to control the transmon, and then you have another transmission line which communicates with the transmon through this readout resonator here. And so here you have a completely linear system with a parabolic potential, and here you have a transmon, the transmon with its cosine potential. And they are coupled, and the coupling will allow you to know whether you are in this state 0 or 1. And you use this transmission line to manipulate the transmon. And then this line is used to reflect a microwave out of this resonator. And the coupling here means that depending on the state of the qubit, the resonator will have two different resonance frequencies. So if you look at the phase here of a pulse that is sent through this transmission line, the phase role is different whether you are in qubit 0 or qubit 1. Note that here I have used a little, there's a detail that counts. Here in this simplified drawing, the transmission line is connected through a capacitance, but here without, in a sneaky way, I have replaced this capacitive coupling with an inductive coupling. This is a division of inductances. It will have a role later. But in any case, whether you use an inductance bridge or capacitance bridge, you have this different phase role for 0 and 1, and by shining microwave at this intermediate frequency here, you will separate 0 and 1. In general, you're going to use in this probe pulse 10 to 100 photons, and the more photons in principle, the higher the speed for the same readout fidelity. Well, all this is good in theory, but in practice, there are some problems. This view of this shift in transition is actually not so simple, because there are some parasitic processes that will happen when you increase the power and you reach to read faster with more precision. So the readout speed is given by this expression here, which involves the average number of photons that you use in the pulse and the damping rate of the readout resonator. And pretty much because the optimum if you want to maximize the information per photon, you have to have this equality here. It turns out the readout speed in the end is proportional to this product of chi, which is the dispersive shift. How much do you shift the resonator per photon, and the number of photon. And this in the following will be the shift delta omega of the qubit when you shine microwave in the resonator. So we want to maximize this readout speed, but something is going to happen when this shift here is going to be too large. Pretty much when the shift becomes of the order of the anharmonicity, which is the difference in transition frequency, bad things happen. And what are these bad things? Well, what happens is that you can use a certain number of photons in your resonator, and by your multi-photon process, a multi-excitation process, you can actually create a certain number of excitation in your system. And so you see that there are many combinations of in this case here, you have 4 photons exciting 5 excitations in the transmon. And this was, for instance, seen in this experiment published by Google 6 years ago. This is actually an example of demolition. Your readout is not the textbook readout at all. It's a demolishing readout. For instance, in this case, you were exciting 6 times the transmon. Okay. So we can confirm that these things happen, this multi-excitation phenomenon happens by Floquet simulation. So this is actually a plot of Floquet simulation. The x-axis is the readout frequency, a tone sent to the transmon, and this is the power measured in a unit of AC Stark shift. The nonlinearity of the system means that when you put more photons in the resonator, you shift the transition of the transmon. And you can see these various lines correspond to these resonances, these multi-photon resonances, and they have this inclined character because as you put more power, you shift down the frequency of the transmon, and so these bad things happen at a slower and slower frequency. And you see that basically, even in the typical readout power, where you shift the frequency of the transmon by, let's say, 5% or so, well, you still have all these accidents. And they seem to get worse and worse as you increase your readout frequency. Actually, you can understand what happens here when you compute the matrix elements between, let's say, the state of the resonator here, and basically what you couple with your resonator, you couple this n variable, the momentum of the transmon, to these states here. So suppose that your resonator frequency is this difference between these blue states here. Then you have to inquire what is the matrix element of charge between this state here at the bottom and the state above here. And that would be, for instance, this line here. And all these dots correspond to what happens when you vary this resonator frequency. And you see that at the beginning, some of these dots increase. So things get worse for certain transitions. In fact, the even transitions get worse. Some they get better, but you have a sort of mess here. But as soon as the resonator frequency goes out of the well, basically your readout frequency can only excite things inside the well to above the well. And those matrix elements decay exponentially when you go up. And the way to understand this is that inside the well, you have the pendulum that oscillates, but outside the well, you have a sort of free running motion of the pendulum. And those wave functions basically tend to have essentially zero overlap. And that's why you have this exponentially decreasing phenomenon. And this is what we have exploited in a new type of experiment. You may wonder, well, do you also get an effect for the readout? Do you have this dispersive shift? And in fact, you find that there's only a mild decreasing effect in terms of this dispersive coupling. So things look good. In fact, this is confirmed by more Floquet simulation, which show you that if you read out your qubit with detuning or frequency that is more or less 12 times above the qubit frequency, you can inspect here the plot, and there's really no possibility of exciting the qubit anymore. And so this is what motivated this new experiment that we did with what we call large detuning, this kind of factor of 10 to 12 in the between the readout frequency and the qubit frequency. We are helped also by a few good things. So first of all, the dispersive shift, even though it tends to decrease with frequency, you're saved by an extra factor here of 4, which is due to the fact that you include more terms in the dispersive shift. So that's excellent. And something that is even better is that this Purcell effect, this sort of loss of coherence because of the coupling with the readout transmission line, is strongly suppressed, and that has a lot of practical advantages. Okay, so we implemented this high frequency readout idea by modifying the transmon considerably. So this is actually the capacitance of the transmon in red here. And the readout resonator, which in most experiments is much larger than the qubit, here is actually quite small. It's a tiny resonator because it reads out at a much larger frequency than usual. And we are coupling this readout resonator to a transmission line in this Hanger mode here. So if you look at our design parameters, you see we have this readout frequency of 9.2 gigahertz, which corresponds to our amplifier chain. And then in this experiment, we went down as low as 760 megahertz for the transmon frequency, while keeping a dispersive shift of order megahertz, which is a sort of standard shift. The quality factor of the transmon at these frequencies is not bad at all. In fact, in general, an observation is that the density of two-level systems is much lower for transmons with low frequencies. So I have to say that we have cheated here. We should have kept the transmon frequency the same, around something like 3 or 4 gigahertz, but of course this would have meant that our readout frequency would have been something like 50 gigahertz or so. So instead, this is the cheating of this experiment. We've kept our readout the same and lowered the frequency of the transmon. This is just a demonstration experiment. I'll talk about increasing the readout frequency for real later in this talk. But let's see what we get. There's a few experimental detail, like the correct thermalization of these transmons with low frequency. We can get very good thermalization with the fridge at 15 millikelvin. There's also the question of the readout pulse that has to be shaped to get the shortest possible time. But here is the experiment in the end. So we check whether we have leaked the transmon in the excited states. And if not, we do a variable duration measurement. And then at the end, we check whether we have a leakage or not. And so by comparing this leakage check before and after, we can get this QND fraction here. And we have plotted an infidelity, a QND infidelity here. So it's the units are in 10 minus 4, so 0.001%. So you see we go much less in infidelity than 0.1% in this experiment. And we see results that make sense. So at first, when you increase the duration of the pulse, you get more and better knowledge. So your infidelity decreases, you learn more, you use more photons, so you learn more. But at some point, you are waiting too long, and therefore you are beginning to be limited by T1. But you see, there is still some remaining effect here. We have not really a perfect readout. There's still some leakage. So, and we investigated this remaining leakage, and it is not actually due at all to this multiphoton excitation. It's due to something different. It's a sort of Raman process. So you have to understand that the junction actually is able to convert microwaves. So you can have a four-wave mixing where you have two photons combining here and two photons going out with the sum of the frequency here being equal to the sum of the frequency there. But you can have also one photon giving out three excitations here. And one main process limiting this readout fidelity is the following. So you can have one photon that's your readout photon. And by a non-elastic process, it can actually excite the transmon twice. And then the remaining photon goes out through this transmission line. And so if this is true, then we should have a predominant leakage to state 2 and 3. And in fact, we can compute exactly all these processes. There's a very interesting formula that was devised by Leonid Glazman and Vlad Korylovich. Vlad Korylovich is the twin brother of Pavel, who did the experiment. It's an interesting breaking of symmetry between twins. So this formula is very, very interesting. So remember, delta omega is your readout strength. And all you need to know is the frequency the environment presents to the transmon a certain impedance. So if you can measure or compute this impedance, you can actually compute this rate of this Raman process. And you get this, this impedance here multiplied by these factors here give you two peaks. There's one peak at the transmon frequency and a peak at the resonator frequency. And your two photon process will mean that this frequency that goes out through the transmission line would correspond to this green line here. So you can compute in advance what will be the strength of this process. And in fact, as you can see, as you will see, it agrees very well with the experiment. So here we've measured the rate of going from 0 into 2, the rate of going from 1 into 3. So these are the experimental points here. You can see that the other processes are completely flat in terms of readout power. They do not change. Whereas here you have this sharp increase. Those two pink lines here correspond to the average photon number and the maximum photon number. Remember, I showed you that we pulse the cavity in a special way. This is just to This is the trajectory of the amplitude of radiation in the cavity. This butterfly shape is due to the fact that we are trying to minimize the time of the readout. And so you see there's an excursion here to, at some point, to a large number of photons. And so that corresponds to this maximum here. So you might think that, yes, you have to do something here. And in fact, the results that agree extremely well with this theory that I presented with no adjustable parameters. So we understand this parasitic process, this remaining process quite well, and we can optimize the parameter of the system to make this quite negligible. So so far that's good. We have a lot of benefits from this high frequency readout. We basically, compared with our competitors, we can reduce this destruction of the qubit state by readout by a factor of 10, pretty much. And this research has also identified a certain number of other inelastic scattering processes, which I don't have the time to discuss, but it leads to, I think, a much better design of the readout mechanism. I would like also to mention that in general, if you want to do parametric operations like 2 qubit gates, higher frequency drive is going to protect you from a certain number of processes that will be present at lower frequency. So this separation of frequency, by the way, is not something super new, because if you think about trapped ions, the difference in frequency between the hyperfine frequency and the optical frequencies is also a great advantage in trapped ions. So we are just applying techniques that are very well known in atomic physics, except that in atomic physics, you cannot weld the wires onto your atoms, whereas here we can. Okay, but the question is, okay, so it looks like we have to very quickly chain our readout amplifier chain and move from 9 gigahertz to something like 40 or 50 gigahertz if we want to keep our frequency, the frequency of our transmon in this range here of a few gigahertz. And of course, if we adopt the transmons of Dave at 100 gigahertz, it will be even worse. But yes, so this is actually a very interesting topic, how to make these new amplifier chains, and we've started to work on that topic with Devoret and Emilio. But we don't really have to, in the first round of experiments, we don't really need to necessarily modify our amplifier chain entirely. We can, if we have a very good mixer, we can introduce this mixer between our readout cavity, which could be at more than 20 gigahertz, but our amplifier chain could be kept in the sub 10 gigahertz regime. So we just need a very good mixer here that would bridge between a very high frequency of our readout resonator and our amplifier chain here. So how do we do that? Well, in the past at Yale, we had devised an almost perfect mixer, this Josephson mixer based on this Josephson ring modulator, which is specialist of microwave engineering will recognize a double balanced mixer here. And this worked in the regime of around 10 gigahertz. Of course, we have to engineer such a ring modulator at a much higher frequency. This is a photograph of our old ring modulator, which was based on 8 junctions. This device was at a very good efficiency. In fact, the efficiency in conversion can be better than 98%. And in amplification, in squeezing, we were able to do experiments basically with really building a nearly quantum limited amplifiers here. So this device is nice, but we need, of course, to engineer it at a higher frequency, which when you look at these SMA connectors here is not trivial. We have to miniaturize everything much more. In the what we have started to do is to use a simplified version of this circuit. So instead of this complicated ring modulator, we can use a simpler circuit, which we have for reasons that are a bit complicated of internal humor at Yale. We have called this device the mutant snail. I can explain why to the people who are interested, but it's a ring. It's a simpler ring. It has 3 Josephson junction and a much smaller Josephson junction in one of the arms of this sort of DC squid. And the idea here is that this dipole, now instead of this quadrupole I showed, it's only a dipole, and it has 2 modes, a common mode, basically where the phase of these 2 junctions here oscillate in phase, and you have a differential mode, and this common mode here, which is the mode A, is a mode with a low frequency, whereas the mode B, the differential mode, is at high frequency, and we can use the coupling between those 2 modes in conversion. So this is actually a 2-tone spectroscopy experiment where you shine a high frequency microwave and you detect it at low frequency. And actually, this curve agrees quite well with the simulation. So we're quite happy that indeed we can realize this coupling. And okay, this is a closer look at the curve. We can test frequency conversion by detecting by essentially measuring, sending some wave at high frequency and collecting the converted wave, and we've studied this as a function of this external flux, and that shows that we can tune this conversion in on a frequency range which is nice to 2 gigahertz of tunability. So that's that was the point 1. Basically, this how are we going to increase the readout frequency? But I wanted now to deal with this. I have just a few minutes left. I would like to also tell you about this question of the number of wires, because of course, when so this was mentioned by Amir, there is a huge problem with superconducting qubits, which is that how do you have a million wires going into your fridge and have these wires controlling all these transmons? And there is, of course, the problem of the wires going from room temperature to low temperature. That's a problem. But even if you would solve this problem, there is also a much even trivial problem, which is just to bring wires into a chip at low temperatures. You have to understand that, for instance, the chip in your laptop has 10 billion transistors, but there's only 1,000 connections. It's very, very hard, actually, even if you have many, many elements on a chip, to be able to bring the wire from the third dimension onto the plane. So there's a terrible problems of wires, even close to the chip. So you have to do what is called multiplexing. You have to have a way, and this is what happens in your computer chip. You have to have more signals traveling on your wires, pretty much, and then you have to fan out these signals so that they address all these qubits. And there are various techniques for multiplexing. And one is this so-called pattern division multiple access. So what this is based on the fact that if you have waveform, oscillating waveform, so A and A prime are the same waveform but shifted by a quarter of a period, you can actually, you can generate this waveform. If you have two waveforms, you can encode a signal with this waveform, and you can get 2 to the n patterns, 2 to the n different patterns. Even if they are not fully orthogonal, that's not a problem. You should be able to encode and decode quite efficiently. And this is, by the way, some techniques that this kind of technique is what is used in cell phones. So the way this works is the following. So if you have ideal mixers, and we need, of course, for control signal going to the fridge mixers that would be as less dissipative as possible. Suppose you have M control channels, and let's say for qubits, you may need channels that would go between 2 and 4 gigahertz. Here I have represented 8 wires with these different channels. You can actually, you can increase the frequency with these mixers, and basically you end up with all these channels being spread between 10 and 40 gigahertz, but you have only one wire. So you have traded bandwidth for the number of wires. And of course, this is the kind of thing that happens on optical fibers. When you have optical fibers going through the ocean and carrying many communications, that it is this sort of technique that is used here. But we have to implement these techniques with the superconducting elements. And so the idea that is if you want in frequency domain, what is happening is that you're taking all these signals here to the 4th gigahertz, and you have basically used them to modulate at very high speed one signal. And you have put all this information into a much larger bandwidth. And of course, you have to do this modulation and demodulation in an efficient way. So you need actually Josephson components that are able to be effective at high frequency. So qubit junctions function in this way. We have this overlap between superconductors. We have this sandwich junction. Ideally, we want a junction that would be made in this way, where you would have one single film, a planar film, and then you would etch the film in the middle and reduce its thickness and use some new phenomenon that makes this reduced thickness superconductor into an insulator. And this is really the work that started, which was started in our group at Yale by Charlotte, and she's now pursuing this here at Stanford. So how do you, what phenomenon can you use to have this transition between superconductor and insulator by just reducing the thickness? Well, there is this hypothetical phenomenon that has been known for a long time. So this is an article by Michael Fisher in the beginning of the 90s. There is, in principle, a superconducting to insulating phase transition that is driven by a phase fluctuations. So this is the phase diagram here. This is temperature. And this axis is somewhat complex. Going in this way, you are increasing the Coulomb interaction between Cooper pairs. How much? I am already over time. We started a bit late, but okay. This is going to be very fast. So here, if you go in this direction here from left to right, you are increasing the Coulomb interaction. But here, in this direction, you are augmenting the superfluid stiffness. And this, if you want a way to think about this effect, is that this material could be thought of as an array of Josephson junction with the islands here having well-formed Cooper pairs. And these Cooper pairs cannot really create superconductivity because these links here are too weak, and there are quantum phase fluctuations which prevent long-range order of phase. Instead, what you have in this regime, you have three vortices here, and the system is insulating. So in view of time, I am going to skip many slides here. And I just want to tell you that we have beginning to have preliminary results that indicate that actually aluminum, niobium nitride films, which have been grown by ALE, but thinned by ALE, seem to be good candidates for this actually superconducting insulator transition and make these junctions that would function at very high temperature. Our data here suggests that indeed we can have we can escape this curse of many experiments on working on this superconducting insulator transition, which tend to find low Q at high kinetic inductance. This new material seems to be really a good candidate for this for a beautiful superconducting insulating transition that would make those planar junctions. So on this optimistic note, I would like to thank you for your attention. Sorry, I didn't fully understand your question. Okay.
Put some sort of filter that blocks all the backscatter photon because they are reflected at a lower energy. Just block all of them. Can you stop this scattering process from limiting your fidelity?
This experiment? Yes. So Yes. So in this experiment, the inelastic process is quite simple and very fundamental. So your readout photon is inelastically converted into a reflected photon with less energy and 2 excitation. There's a possibility of engineering this resonator here to suppress this intensity here. But what you're alluding to perhaps is that in the environment, if you don't, there's a question of microwave hygiene here. If you would have in your environment other degrees of freedom that could accept this photon here, this inelastic photon, you could enhance the process. So indeed, in order to limit this kind of nonlinear effect, this inelastic scattering of your readout photons, you have to engineer the environment in your readout very carefully. So that's why, for instance, indeed, the challenge here is that you should control really very cleanly all the modes of your system at higher frequency.